Welcome to DET-TRONICS Technical Brief number 530, Troubleshooting an Eagle Quantum Premier or EQP Heartbeat Diagnostic LON Fault. This video will explain the root cause of a loss of heartbeat LON fault, common causes of this LON fault, diagnostic tools, and techniques used to troubleshoot and clear this LON fault. Let's get started. LON faults are always caused by continuity issues. A LON fault can be initiated by an issue with either wiring or data continuity. You should already know that the EQP system uses a ring topology. The ring starts and ends at the EQP controller, which is perfect for continuity checks. There is already a technical brief, number 510, on the continuity voltage diagnostic, which is a diagnostic that checks to make sure the wiring is correct. A very simple explanation of this diagnostic is that the voltage is injected at COM1 of the EQP controller and then measured at COM2 to ensure it made it around the ring. You should view technical brief number 510 and verify you do not have any wiring issues before attempting to troubleshoot a fault caused by data continuity, which this video covers. A simple explanation of the data continuity diagnostic is that a data packet called the heartbeat is transmitted out of each of the controller's COM ports 4 times a second and listened for by every device and the other COM port. A LON fault is initiated if either a device or the controller does not see a heartbeat for 5 seconds. And depending on certain factors, the devices may or may not go into an isolation routine using their isolation relays to isolate the fault. The heartbeat is the hardest working diagnostic. Its job is to navigate through every inch of the network and every device on the network. As I just stated, the heartbeat is transmitted 4 times a second, alternating originating COM ports. Data from each device is also being transmitted on the network. Here is the EQP S3 software LON diagnostic page for a fully functioning LON network. All the devices blink changing colors as they alternate communicating with COM1 and COM2 of the controller. When something happens where the heartbeat does not make it around the network, the devices will start locking into the COM port they are successfully communicating with. Depending on the severity of the missing heartbeat, the EQP S3 software LON communications page may look like this, where you can see the devices are blinking but not changing color as they are locked into communicating with the port that works for them. Address 7 through 30 are locked on to communicating with COM2, the others with COM1. If the heartbeat loss is severe enough that one or more devices are not receiving the heartbeat from either COM1 or COM2, the device will go into a fault isolation mode using its isolation relays. If this happens, you will see one or more red bars on the S3 LON diagnostic page. The possible causes for the loss of heartbeat is attenuation of the heartbeat as it travels through the network. The loss of the heartbeat could be because of interference. This is where electrical noise from something outside the LON network is being coupled onto the LON network and is distorting the heartbeat beyond recognition. The loss of heartbeat could simply be from a defective device. And the last cause covered in this video is from impedance mismatches on the LON network. The symptom of this problem is similar to interference, as an impedance mismatch causes reflections on the network that can clash with communications, distorting them beyond recognition. Before we start with the possible causes of the loss of the heartbeat, I need to mention the EQP controller log file, as it will be referenced later in this video. This is a log or event file that is stored in the EQP controller. It can hold up to 4,096 events, such as power up, devices offline, or COM faults, so can be quite helpful when troubleshooting. The log file can only be accessed and or downloaded using the S3 software. Please reference technical brief number 550 on how to access, download, and save the file. Now, let's start learning about the causes of the loss of the heartbeat. Attenuation is where signal strength is weakened so much the heartbeat is not making it around the network. It is typically caused by a problem with network engineering, long runs with too many devices, or excessive resistance due to loose wires, a device issue, or corrosion. It is difficult to see if attenuation is the cause of the loss of the heartbeat without specialized equipment like an oscilloscope. If you do have an oscilloscope, you need to verify the communication signals are at least 400 millivolts in amplitude. If the signal is above 400 millivolts at each controller COM port, attenuation is not your problem. If it is below 400 millivolts, you need to find out whether it is due to network engineering or excessive resistance. Let's look at the general network engineering rules first, as it doesn't require special tools or diagnostics to see if the network is engineered/installed within these general rules. We know that networks with long runs or networks with lots of devices can attenuate or cause distortion of the heartbeat, thus the loss of the heartbeat. There are devices such as a network extender, used to condition or sharpen communications, that can become small and distorted, and there are repeaters that are just used to repeat communications, can help in these situations. Here are the general rules for network extenders and repeaters for highly populated networks or networks with long cable runs or both. Assuming the correct impedance cable is used and there is no electrical noise, a network extender should be installed after the first 60 devices or 2,000 meters, and then every 40 devices or 2,000 meters after that. There is a maximum of 6 network extenders per network. Physical network repeaters can also be used to strengthen the network. They don't condition the signal like the network extender, only amplify. The installation rules for repeaters are that only one can be installed between the controller and the first network extender, and up to 2 between network extenders. The maximum number of repeaters per network is 14. Another way to check to see if attenuation is your problem is to check for excessive resistance by ohming out the network. You are going to have to disconnect the LON network to do this test. So first, remove the power from all standard LON devices. You must remove the power from these devices as they will not see a heartbeat with the LON disconnected and go into fault isolation mode, opening and closing its relays. So if you are trying to ohm out the network and you see the ohm reading spiking on and off, you still have power on a standard device. Network extenders and repeaters do not have isolation relays, so they can be powered or not powered when checking resistance. Let's look at what you should be reading when testing the resistance of the network. First, there will be some resistance in the LON network cable. It is 18 gauge wire, which has an approximate resistance of 8.3 ohms per 1,000 feet. I was told this network is 2,000 feet long. 2 times 8.3, the resistance of the network wire is around 16.6 ohms, if I was told the right length of the network. Next, let's look at the typical resistance per device. Standard devices have LON isolation relays that are de-energized, so they are at 0 ohms. Network extenders and repeaters both ohm out at around 26 ohms each. So with the power removed from the controller and the LON network disconnected at each end, you should check the resistance reading A to A. There is around 16.6 ohms of wire resistance plus 26 ohms for each network extender and repeater. There is one of each, so that is 52 ohms, so I should be reading around 68 ohms. I am actually reading about 70, so that looks good. Then check B to B. It should be very close to the A to A reading. It is. And then finally, check A to B. You should be reading infinite ohms. If any of these measurements don't look good, you will need to start segmenting the LON network to find out where the resistance is. Here is a quick hint on segmenting the network. Power down the network and devices. Disconnect the LON wires from the controller. Pick a spot about halfway around the network and disconnect it. Short the 2 wires you just disconnected. Take a resistance reading at COM2. The reading is 69.5 ohms. You now know 2 things. First, you are on the COM2 side of the network, and 69.5 ohms is close to what you should be reading. 1,000 feet of wire out, 1,000 feet back, and 26 ohms for each way through the repeater. And since you are there, do a resistance check on COM1. It should be infinite. If not, you have a problem on the COM1 side of the break of the network. One more tip on segmenting. Take the two wires disconnected halfway around the COM2 side of the network. Short them together and connect the two to earth ground. Not the shield, earth ground. Now check the A wire at COM2 to earth ground. Here is 35 ohms, which is close to what I should have. 26 for the repeater and 8 for the wire. And then check the COM2B wire to ground. It should be close. And then you can do the same thing on the COM1 side of the network. It is almost impossible to tell if interference is causing your LON fault without a minimum of having a LON protocol analyzer to look for corrupted data packets, or the EQP S3 software, as interference typically causes many other problems such as devices intermittently dropping offline. At DET-TRONICS, we use the Loitec LON protocol analyzer to look for interference. You don't have to be a LON expert or a rocket scientist to interpret the results of the LON protocol analyzer. You just need to look at the number of corrupted packets on the statistics page. The LON controller file is the next best tool to use. If interference is causing the LON fault, you could see any of these events and often multiple of the same. One thing you can find that is somewhat unique to an interference problem is that the entries in the log can be cyclical. Maybe every 4 hours, maybe every day at the same time, as a piece of large machinery in a processor transfer can start at the same time every day, or a motor in a batch application can turn on at a certain time every day. So look for events that are cyclical. The EQP S3 LON diagnostic page is another tool to use. If interference is causing the LON fault, you could see something as simple as a device or devices losing communications, or whole pieces of the network dropping off. Troubleshooting the source of the interference can be difficult, as the source of interference may not be exactly where the noise is being introduced. Again, segmenting the network or disconnecting segments one at a time is typically the way to find out where the interference is being introduced. Saying that, the most common source of electrical interference is from variable frequency drives, or VFD drives. The control signal for these drives is typically a square wave that varies in frequency and amplitude that can be in the hundreds of volts. There are multi-jacketed shielded cables used to connect the drive controller to the motor to lessen interference with other electrical equipment, but if the end user does not use drive cables like this, or does not tie the shields to ground, the large signal can couple to the LON network, causing a lot of interference. To lessen the effect of electrical interference coupling onto the LON network, use the recommended long cabling. Cut the shields back and insulate. Insulate the drain wire all the way to the connection terminal block. Make sure the drain wires are all connected to the shield connections at the devices and controller. And finally, ensure the drain wire never touches the device housing or cabinet. One other thing to check is the cable tray the LON network cable is laying in. It is best to ensure the LON network cable is not laying in with other large cables that could possibly be carrying high voltage machinery signals. Having the LON network in a separate cable tray would be ideal, but at a minimum, the LON cable should be as far away as possible from any other large cables in the cable tray. It is not very common, but a device could cause the heartbeat being lost. Standard LON devices have a straight-through connection via their isolation relays and don't have any active components connected directly to the LON network. It would be the least likely of the 3 network device types to be causing a problem. Saying that, they could have an internal failure or an isolation relay causing some problems, but far less likely to cause a problem versus a network extender or a repeater that have active components directly connected to the LON network and process every communications passing through them. You could swap out the network extenders and repeaters, as there is no configuration nor network address to set, to see if that fixes the problem. It is not recommended to start replacing standard devices, as it is labor-intensive to configure the new device the same as the old, especially ensuring it has the same network address. And then there could be an inadvertent system alarm, as some output devices could be configured to trip if there is a loss of power, and you are going to have to remove power to swap out the device. It is best to try ohming out suspect devices first. That's good. That's good. That's good. That's good. And if that is okay, try jumping the LON network around the devices. Disconnect the device completely from the network and then jump A to A and B to B. Using cable with the wrong electrical characteristics will cause communication reflections that could crash with and distort normal communications to an unstable state, very similar to the interference just covered, with similar results, product or products intermittently dropping off the network. And you would also see similar errors or events in the EQP controller log file. So selecting a LON network cable with the correct electrical requirements is just as important as selecting one with the correct physical or mechanical requirements. Here are 3 cable types DET-TRONICS recommends. The important electrical characteristics is cable capacitance, as the more capacitance, the more sharp edges or digital communications around, and impedance, as incorrect impedance will cause reflections. The required impedance is 100 ohms, as every LON device or termination is 100 ohms. And when everything is matched, the signal sails through the LON network with little loss. Communication reflections happens anywhere there is a mismatch of impedance. The amplitude or strength of the reflection is dependent on how big the mismatch is. And the stronger the reflection, the more it can distort other communications on the network. So if the cable used is not 100 ohms, there could be reflections traveling all over the LON network. This is what happens if there is an impedance mismatch. There is a reflection at every junction of the mismatch. You can see there could be a lot of reflections traveling throughout the network, causing mischief. Where we often see a mismatch of cabling is where additional devices have been added to the network. For example, everything seems to be working fine in this network, and then an additional device was added without using the proper cable. So now there is going to be a reflection where the new cable is spliced in. As with interference, the recommended tools to find out if reflections are causing the LON fault is the Loitech Protocol Analyzer to look for corrupt packets, and the EQP S3 software to see if device or devices are dropping offline. But then there is one additional tool for impedance reflection issues, the network extender. It can act as an impedance matching device, so you can add a network extender to a troublesome area and it will take care of the reflection. This is a good application for a network extender. Try putting 1 or 2 extenders in where the network is spliced, but remember, the maximum network extenders per network is 6. Figuring out if the LON fault and devices dropping offline is being caused by interference or reflections being caused by impedance mismatch can be difficult, as there are a lot of things to think about. But here are a few things to look for. If there are devices or groups of devices dropping off a relatively new network, it could be either. You will need to look at the cable specifications to see if it is 100 ohm impedance. Check to make sure the installer cut back the shield and insulated it, and the drain wire is insulated and connected. If that looks good, it is time to find out if there are any variable frequency drives or large electrically driven machinery in the vicinity of the network that could be causing the interference. If this is an established network, ask if they have performed any maintenance on the network, extended it, shortened it, added, or removed devices to ensure they all are wired or terminated correctly. And then ask if there is any large electrically driven machinery that has been installed lately. This video was developed by DET-TRONICS Educational Services. Here is contact information if you have comments or you would like more information.